Unit 3, Day 2 continued. We are continuing on graphing our rational functions. So for this first one, remember when we are graphing our rational functions, the first thing you want to do is factor the equation. So go ahead and the numerator just stays as x, and we have x minus 2 times x plus 1 to factor. As you can see, there are no common zeros between our numerator and denominator. So to find the domain, remember it's the zeros of the denominator. So what makes my denominator 0? X minus 2 equals 0. So x equals 2. And x plus 1 equals 0. So x is equal to negative 1. So that means our domain is going to be all real numbers except for 2 and negative 1. And this is how we would write it. So now I have the domain. Those values also help us figure out our vertical asymptotes or holes. So because there are no common zeros between my numerator and denominator, I know that at x equals 2 and negative 1, those are both vertical asymptotes. There are no holes. And even if you were to plug 2 and negative 1 into your simplified answer, which this doesn't simplify at all, it still makes our denominator 0, which is how we know, again, it's a vertical asymptote versus a hole. So for the x-intercepts, remember the x-intercepts are the zeros of the numerator, as long as they're not zeros of the denominator. So the only thing we have in our numerator is this x right here, so x would just be equal to 0. So that gives us a y x-intercept 0, 0. And if the x-intercept 0, 0, that means the y-intercept is also 0, 0. But you can confirm by plugging 0 in for x. That's how you find your y-intercept in solving. So if I plug 0 in for x, notice that I would get 0 over negative 2, which is just equal to 0. 0 in the numerator is okay, remember. So now for the horizontal asymptote, I look at the degree of the numerator, which is 1, over the degree of the denominator. So remember, if it's in factored form, you have to add it together. But if it's in standard form, you can look at the highest power of x. So degree 2. Because the numerator degree is less than the denominator degree, that tells me I have a horizontal asymptote at y equals 0. And that also gives me the end behavior of my function. So as x approaches either positive or negative infinity, I know that my y values are going to be approaching 0. So for my graph, I'm going to go ahead and graph my asymptotes. I have vertical at negative 1 and 2, and I have a horizontal asymptote at 0. So for this graph, that means we have 3 different areas we're concerned about, because remember, you always want to graph to the left and the right of your vertical asymptote. So here, that means we have the 3 different portions. Notice that I also have an x-intercept of 0, 0. So because this x-intercept crosses over my horizontal asymptote, it means I need to figure out what's happening to the left and right of this point. So there's actually 4 regions we're concerned about. So you're asking yourself, well, I thought we weren't allowed to cross over our asymptotes. That's only for vertical, because vertical asymptotes make your denominator 0, which we can never have. Remember that horizontal asymptotes are talking about your end behavior. So this middle portion of my graph does not tell me what the ends of my function is doing as x gets very large in the positive or negative direction. So it doesn't matter that we're crossing over horizontal, but we can never cross over the vertical. So I'm going to use my big little concept in order to help me graph, see what the graph is doing to the left and right of the vertical asymptote here. So this is a vertical asymptote at x equals negative 1. So something to the left of negative 1 but close to negative 1 would be negative 1.1. And so if I were to think about the big little concept, I always use my factoring form to help me. And I'm just looking at the signs to tell me if I'm going up to positive infinity or negative infinity. And we talked about the big little concept the other day. So if you need to go back and look at that, you can. So we have negative 1.1, which is a negative number, over negative 1.1 minus 2 would be a negative number. And negative 1.1 plus 1 is also a negative number. So negative times negative is positive, so that gives me a negative over a positive answer. And of course, when we're dividing a negative by positive, that means we're going to be going towards negative infinity. So I know that as my x values get closer to this vertical asymptote from the left side, we are going to be going down towards negative infinity. So again, you don't just drawing a sketch of the graph, so we just know that we follow our asymptotes when this happens. Could you actually pick an x value such as -2, plug it into the function, and figure out what the y value is and make a table? Yes, that would be fine too. It just might take you a little bit longer. So now let's go ahead and look at the right side of this vertical asymptote. So something to the right of this vertical asymptote but close to it would be -0.9. And again, I'm using my factored form to help me figure out where this is going to go. So in my numerator, -0.9 would be a negative number. -0.9 minus 2 is also a negative number. And -0.9 plus 1 would be a positive number. So negative divided by negative gives me positive. So that tells me this side is actually, as we are approaching this asymptote, going up to positive infinity. So my graph would go up this way. Could I also plug in -0.5 into my function for x and figure out the y value? That's fine too. All right, so I just move that up to the top so we don't get confused with the next asymptote. So the next asymptote we know is at an x value that is equal to 2. So we're going to look at the left and the right of 2 using our big little concept. So something to the left of 2 but close to 2 would be 1.9. So if I think about plugging 1.9 into this function, 1.9 in the numerator would just be a positive number, and 1.9 minus 2 is a negative number, and 1.9 plus 1 is a positive number. So if I have a positive divided by a negative, that tells me I'm going towards negative infinity. So that means as we're approaching this vertical asymptote of x equals 2, that means the closer and closer I get, the larger and larger negative numbers I'm getting. So I'm going down towards negative infinity here. So now we need to figure out what's happening to the right side of my graph. So on the right side of my graph, something close to 2 would be like 2.1. Of course, we could get closer values like 2.01, etc. So if I plug 2.1 into that function, I get a positive number. 2.1 minus 2 would be a positive number. And 2.1 plus 1 is also a positive number. So that tells me I'm going towards positive infinity. So that means I would be in this upper region of my graph. And again, you're just going to follow your asymptotes. So now that I have the graph, let's go ahead and just double check using our graphing calculator. So in my graphing calculator, I plug this into my y equals, which it already is. And once I plug it in, I'm going to go ahead and hit graph. And now we can see that our graph looks like this graph. And again, had I plugged in x values to see what the y values are, that's fine. It just might take you a little bit longer. So if I would have plugged in an x value of -2, I would have gotten -5, and I could have plotted that point on my graph. And then I would have to figure out something in between 0 and -1, so I would have had to plot -0.5 to get that. And then if I look here, you can see you have 0, 0 on your graph, even though it crosses over your horizontal asymptote. If I would have plugged in 1 into my function, I get -5, so that's the negative region here. And of course, values to the right of this vertical asymptote of x equals 2, notice these are all positive. So that's how we know we were on the upper region. So I use the big little concept to help me with that. But again, you are always welcome to plug in points for x and figure out the xy coordinate and then plot them. It just, like I said, may take you a little bit longer. So let's go ahead and look at the next function. So for the next function, we have, again, to first factor this before we do anything. So when I factor my numerator, I can take out an x, so that's x times x minus 1 over x plus 1. There are no common zeros, so that doesn't simplify, but remember that our domain is the zeros of our denominator, so x plus 1 equals 0, so x is equal to -1. So that tells me my domain is negative infinity to -1 and -1 to infinity. And that means that because there are no common zeros, it's a vertical asymptote at -1 and not a hole. We don't have any holes. My x-intercept are the zeros of the numerator. So in this case, I have 2. I have x equals 0 because of this x right here, and I get x minus 1 equals 0, so x is equal to 1. So I have 0, 0, and 1, 0. Because of 0, 0, that tells me that's the y-intercept. But again, you can always use your factored form or your original equation to find the y-intercept by plugging 0 in for x if it helps you to see. We would get 0 over 1, which is just 0. And the horizontal asymptote, in this case, the degree of the numerator when we're in standard form is 2, and the degree of the denominator in standard form is 1. So now notice the numerator degree is larger than the denominator degree, which means there is no horizontal asymptote. So notice the degree difference between the numerator and denominator is 1, which means we're going to get a slant asymptote. And recall, to find your slant asymptote, you need to use long division or synthetic division because we're dividing by a linear binomial where the coefficient in front of this x is 1, we can use synthetic division. So for synthetic division, remember it's the 0 of the denominator goes in the box, which in this case the 0 of the denominator is -1. Then you use your numerator. It has to be in standard form, and if you're missing any 0 placeholders, make sure to add those in, and we use a coefficient. So 1, -1, we're missing a 0 placeholder for the constant term, so I got to put that there. For synthetic division, remember we're always adding, so bring down that first term, which is 1. 1 times -1 would be -1. -1 minus 1 gives me -2. -2 times -1 is +2, and this last number is always your remainder. Because this is a degree 2, that means our x's start off with degree 1, so this would be x minus 2. So that tells me my slant asymptote is at y equals x minus 2. So don't forget to write that y equals. Just like our vertical asymptotes, we have to write x equals. For our horizontal or other asymptotes, we have to write y equals. So now on my graph, I can go ahead and start to graph this. I have my asymptote for my slant is at a y-intercept is -2, and the slope is 1. So I'm just going to go ahead and graph that. Now that I have that, I have a vertical asymptote at x equals -1. And now I can go ahead and figure out how to graph my function. I can use my x and my y-intercept to help me. So 0, 0, 1, 0. So that's nice because to the right of my vertical asymptote, I know my graph is going to be in this upper region. And of course, you always follow your asymptotes. So it goes this way. To the left, I don't know where it's going because I don't have any points over there. I know that it's not going to be on this region over here because I don't have any other x-intercepts. But again, if you didn't know that, you could always use your big little concept or plug in a number to see what the value is going to be. So something close to -1, but to the left of -1 would be -1.1. When I plug that into my factored form, which is up here, I would be plugging in a negative number because that's -1.1 for x. -1.1 minus 1 is also a negative number over -1.1 plus 1 is going to be a negative number. So notice that means I have a positive divided by a negative, which means we're going to be going down towards -infinity. So as I approach this vertical asymptote, my values are going towards -infinity, and then it's just going to wrap around and kind of look like the other side. So now I have my graph. For the end behavior, remember the end behavior is following your slant asymptote. So in this case, let me go ahead and move this a little bit. So in this case, my end behavior would be as x approaches positive infinity, my y values are f of x. Notice that they're going up here to infinity. And as x approaches -infinity, my y values are going down here to -infinity. Because remember, they follow your slant or horizontal asymptotes, in this case slant. So look at the slant asymptote. Remember, we learned about polynomials last year. This is odd polynomial with a positive leading coefficient, so it means it goes up to the right and down to the left, and we can see that from the line that we actually graphed. And so that would be it for this. So I went ahead and plugged this into my calculator along with the asymptote so that you can see it's a little bit thicker so you can see the end behavior. So when I hit graph, here's the actual graph. And then next it's going to graph my slant asymptote so you can see my end behavior is following that slant asymptote, but this is what our graph would look like. All right, we have one more problem to do. So again, first things first, we're going to want to go ahead and factor my numerator and my denominator if possible. So in my numerator, that's the only thing that actually factors. So x minus 2 times x plus 1 over x minus 1. Again, I don't have any common zeros between my numerator and denominator. So the 0 of my denominator is equal to a value of 1. So that means my domain is -infinity to 1 and 1 to infinity. There are a vertical asymptote at x equals 1 because there are no common zeros between the numerator and denominator, so there are no holes. My x-intercept is the zeros of the numerator, so x minus 2 equals 0, so x is equal to 2, and x plus 1 equals 0, so x equals negative 1. There are no common zeros between the numerator and denominator, so we don't have to worry about that. So we have a x-intercept at 2, 0, and negative 1, 0. My y-intercept, I plug 0 in for x and solve, so 0 squared minus 0 minus 2 over 0 minus 1 gives us negative 2 over negative 1, which is 2, so I have a y-intercept of 0 and positive 2. In this case, my degree of my numerator is 2, and the degree of my denominator is 1, so that means the numerator degree is more than the denominator, so there is no horizontal asymptote. And again, the degree difference is 1, so that means there's going to be a slant asymptote. So again, to find the slant asymptote, we can use the long division or synthetic division. Because we're dividing by a linear binomial, we can go ahead and use our synthetic division. So the 0 goes in the box, which is 1 from the denominator. Then we have our coefficients of our numerator, so 1, negative 2. Bring down that first term, so 1 times 1 is 1. This gives me 0. 0 times 1 is 0. So my remainder is negative 2. Because the degree of the numerator is 2, that means this starts off with a degree of 1. So that would just be x plus 0. We don't need to write, so just x. So that means my slant asymptote is at y equals x. So for my end behavior, this is an odd polynomial with a positive leading coefficient. So I know that my end behavior is going to go up to the right and down to the left. So as x approaches infinity, my y values will be approaching positive infinity. And as x approaches negative infinity, my y values approach negative infinity. So let's go ahead and graph this out. So our asymptotes we'll graph first. So we have a slant asymptote at y equals x, which has a y-intercept of 0. And then we have a vertical asymptote at x equals 1. And we can go ahead and start to graph this. So it looks like I have x-intercepts at negative 1, 0, and 2, 0, and a y-intercept of 0, 2. So this is nice because on the left and the right side of my vertical asymptote, I have points. So I know that my graph just follows along my asymptotes. And so this would be the graph of my function. And as you can see, for your end behavior, as x values get very large, it's going up this way in the positive direction. And as x values get very large in the negative direction, we're going down towards negative infinity. So that's why this was our end behavior. And of course, we could always graph this in our graphing calculator to double check our work. And so that's it for our graphs of rational functions, and so now we've also graphed our slant asymptotes.